Question 26, Jan 2023 past question, physics. The fundamental frequency of an open organ pipe is the same as that of the second overtone of a closed organ pipe of length 0.2 meter. What is the length of the open organ pipe? First, to study sound wave in the laboratory, we use several instruments which are called sound instruments. One of these instruments is the organ pipe. So just like the normal domestic pipe that we use at home, it can be in form of metal or plastic. Now, this organ pipe is into two types. We have the open organ pipe, such that the two end of the pipe will be open. And then we have the closed pipe, in which one of the end will be open and the other will be closed. Now, for the open pipe, just like the question says, for the open pipe, the simplest form of wave that we can obtain in an open pipe will go in this manner. This is the simplest form of wave that we can obtain. Now, this part is this end where we have open end. It's known as the point where we have the maximum disturbance, and it is the antinode. Here we also have another antinode. Now, this point with zero disturbance is known as the node. Now, the distance between two successive antinodes in normal wave is taken as lambda divided by 2, where lambda is the wavelength of the wave produced. Now, this corresponds to the total length of the organ pipe, or the air column inside the organ pipe. Now, in this case, this simplest form of wave would produce the smallest frequency, that is the minimum frequency of the air column. So right now, the minimum frequency, which is F0, is calculated by using the formula F0 equal to V all over lambda. If I substitute for lambda here, I can find the value of lambda from here. Since L equal to lambda over 2, make lambda the subject of formula, that will give me 2L. If I put 2L here, that means the fundamental frequency will be equal to V all over 2L. This will give me the minimum frequency. Now, if we go one more again, so that's what they call, if we produce more loops inside the air column, if we produce more loop inside the pipe, more loop of air, so that means we will have the second harmonic. This fundamental frequency is also known as first harmonic. We have the second harmonic, which is the same as the first overtone, or the third harmonic, which is the same as the second overtone. Now, to get those ones, we just be using the integral multiple of the first harmonic. So F1, which is the second harmonic or first overtone, will be given as 2F0. We continue like that. F2 will be given as 3F0. That is how it happens. It continues like that. This is how it happens in an open pipe. Now, for a closed pipe, the smallest waveform that we can have will go in this manner. So this is how it goes. Any sound wave or air that is coming from the open end will be incident on the closed end and be reflected back again in this manner. So this part where we have zero displacement is known as the node, and the open end we have the antinode here. Now, the distance between a node and the corresponding or the successive antinode is taken as lambda divided by 4, and this corresponds to the total length of the air column. So I can say from here that L equal to lambda over 4. If I make lambda the subject of formula, I will have 4L. So to get the fundamental frequency over here, F0 will be equal to V all over 4L, just like we derive it from here. Now, for this one, this is not actually what they ask us to do. They ask us to use the second overtone in the closed pipe. Second overtone. Now, for a closed pipe, if you want to get the overtones, you'll be using odd number multiple of the first of the fundamental frequency. So this is how the diagram of a second overtone will look. Okay, for a first overtone will look like this. First overtone will look like this. Oh, sorry. Second overtone. First overtone will look like this. This is first overtone. First overtone. Then if we go like two more times, that will give me the second overtone. Two more times, I will have this. I will have this. So that means I will have node here, an antinode will occur here, another node here, antinode here, another node here, and antinode here. So for the first overtone, which is F1, that will be V all over, that will be F1 will be equal to 3F0. Since I said it is the odd multiple, that means F2 will be equal to 5F0. So that is how it goes. So this is the one that I need. That will give me 5V all over 4L, according to what I need, what we derive from here. Now, I want to equate this second overtone to the fundamental frequency of the open pipe. So let's see how that will go. Let's substitute. So F0 of the open pipe is equal to second overtone of the closed pipe. Let's substitute what we have. So first fundamental frequency of this is equal to V all over 2L. Let me indicate L0. Let me put L0 so that it will mean the length of the open pipe. So that will be equal to 5V all over 4L, which is the second overtone of the closed pipe. Now from here, I can make L0 the subject of formula. First of all, V can cancel V. That's if I divide both sides by V. Now, they gave me L from here as 0.2. So I will have 1 all over 2 L0 equal to 5 all over 4 bracket 0.2. Now, this will give me 1 all over 2 L0 equal to 5 all over 4 times 0.2. That's 0.8. 4 times 0.2, that will give me 0.8. 0.8, let's cross multiply. So that will give me 0.8 equal to 5 times 2L0. Divide both sides by 5 times 2L0. L0 will be equal to 0.8 all over 5 times 2. This is 0.8 divided by 10. This is 0.08 meter. So this will give me the length of the open pipe, which is corresponding to option D. Thank you.